tomorrow is actually, it's almost a trivial lesson because we're doing the reciprocal trig functions in tan. We're doing the derivatives of those. We do the derivative of sine and cos today. We're doing it by using the difference quotient for sine and then just using identities to develop cosine. So I'm going to ask you probably on the test to possibly reproduce the derivative of sine from first principles, which means going through the difference quotient. To do that, there are a couple of limits that I will give you, as well as a couple of identities that I'll give you right on the test, okay? So this limit as h goes to 0, not n goes to 0, of cos h minus 1 over h is 0. So if you've done the preamble, you know that that's what happens, right? Similarly, this limit as h goes to 0 of sine h over h tends to 1, okay? And we have to take the limits because both of these result in a division by 0. If you haven't taken advanced functions, you don't recognize this angle sum identity, okay? The sine of angle x plus angle h is equal to the sine of x times the cosine of h plus the sine of h times cosine of x. Okay, so this is one of the identities that we use when we're doing the difference quotient to determine the derivative of sine from first principles. So you can see the h is in there because we're going to be taking the limit as h goes to 0. And yeah, you'll see how it turns out. Okay, now there's a second thing we're going to do. Once we get the derivative of sine, we are going to use some of the cofunction identities to come up with the derivative of cos, and just to do it very, very easily, okay? So this is y equals cosine of x. And really, it is just the sine curve shifted to the left pi by 2 units, okay? So this is one of the identities that we're going to use. And we're also going to use the identity where we shift it to the left yet again, and we reflect it in the x-axis. So we'll use those two identities when we develop those. Okay, so that's that. Those are sort of the identities that we're going to use when we develop the first principle sine function. Then we're going to do 2 sample problems. So the derivative of sine x with respect to x. Well, we all know that's just the limit as h goes to 0 of sine of x plus h minus the sine of x all over h. Here's my meter stick. There we go. There's our difference quotient. But sine of x plus h, I can write in an identical expression, sine x times cosine of h. Put brackets in there to keep it from turning into hyperbolic sine and cosine. And then we're going to do plus the sine of h times cosine of x. And then minus sine x, just like before. This whole thing. Yes, so you will actually have to reproduce this on Friday's test. This is exactly what you're going to do. Okay, so this is a bit of a song and dance, but I do like this particular proof, even though it involves sort of these awkward things. Okay, there's a sine x here, and there's a sine x way down here. I would like to factor a sine x out of those two expressions. So just to make it a little bit easier to see, I'm going to move that sine x that's way down there to there. Just popped up there. And because I can do addition in any order, I forget what they call that, associative, commutative, I never know. That's okay. I can do it. I can move it around. Do you need to write down that step? The question is, do you need to write down that step? And yeah, that takes like 30 seconds. So let's just, yeah, you mean like just go ahead, put it all together and factor it? That's what we're going to do right now. We're going to factor sine x out of here. I'd like to see that step in between. This will be a real hup one too. If you're writing it down, I wouldn't worry about it too much. Okay, sine x, I'm going to factor out of this, which is going to leave cos of h. minus 1. That looks like an identity that I know. Plus sine h, sine of h times cosine of x. And combining two steps together and putting giant brackets around this whole expression, I'm going to break it apart and put an h underneath both of those. Okay, so in this kind of a reverse adding fractions, I'm going to add those two things together as separate entities. And you'll see why, because I'm going to apply my properties of limits to this whole thing. The limit of a sum is equal to the sum of the limits. Okay, so that's my first step. I'm going to break this into two limits. So this is the limit as h goes to 0 of sine of x, times cosine of h minus 1, plus the limit as h goes to 0 of the sine of h times cosine of x. And this is all over, both of these expressions are over h. And that's a really tall h there. There we go. Okay. So now I have a new limit, or two limits added together. Limit of a sum is the sum of the limits. And similarly, the limit of a product is the product of the limits. So I'm just going to break these apart. So I'm going to do the limit as h goes to 0 of sine x times the limit as h goes to 0 of cosine of h minus 1 over h. And very sneakily, I know what that limit is, so that's okay. And this is the limit of sine h over h as h goes to 0 times the limit as h goes to 0 of cosine of x. Okay, so I haven't really cheated, but I've just moved the denominator underneath there. And that happens to be because I know what this limit is. And I know what this limit is. Because I painstakingly put little numbers into a table a little while ago. I know what those limits are. Know your limits. Since we know these limits, we're getting rid of that h going to 0 issue. Limit as h goes to 0 of sine x. Well, there are no h's in there, so that's just sine x. The limit as h goes to 0 of cosine of h minus 1 over h. That turns into a 0, thus making the whole first part of this expression turn into 0. Making it go away, which means it's simpler. Okay, this is not an n, this is an h. The limit as h goes to 0 of sine h over h is 1, which often is so trivial I don't even write it. Although 1 is a very important number, times cosine of x. And so the derivative of sine x is the cosine of x. Pretty simple. The derivative of a periodic function is another periodic function, and I think that makes sense. Okay, now all we need to do is find out what the derivative of cosine of x, and the entire world of trig derivatives is unlocked. Simple harmonic motion, all that kind of stuff. So I'm very gingerly going to erase the sine x, and I'm going to take the derivative of cosine of x. And I can't do that because I don't know what the derivative of cosine is, and I don't want to go through all that work of doing the difference quotient again. That's just a lot of trouble. But I do know that cosine of x is really just the sine of x shifted over 90 degrees to the left. So instead, here's what I'm going to do. I'm going to take the derivative of the sine of x plus pi by 2. I'm going to find out what that is, and then I'm going to see if I can simplify it a bit with another identity. Okay? Same thing. doing the same thing. It's identical. It's continuous everywhere, so there's no weirdness is going to pop out on me. Okay. Hey, what's the derivative of sine? Cosine. Yeah, easy. Okay. Yeah, so it's the derivative of cosine of x plus pi by 2. Now, theoretically, this is a chain rule question, but really it's not. Because what's the derivative of the inside function? The derivative of x is 1. The derivative of pi by 2 is nothing. So, yeah, it's just this. Okay. Now, that's okay, but it's not completely beautiful yet. So let's see if we can beautify this a little bit. Okay. So here we go. Here's the, just really hot dogging it. Here's cosine. Woo! Okay. And here is, so this is y equals cosine of x. And let's just shift it over pi by 2 units. So this is it here. Woo! Yeah, something like that. Okay, so there we go. This is y equals cosine of x plus pi by 2 units. Now the good news is this is just y equals negative sine x. So it's another identity. Oh, I know you can't see that. Okay, y equals negative sine x. So it's actually just another identity. Okay. So the derivative of cos x is just negative sine x. That's it. We know the derivative of cosine. We know the derivative of sine. We can use it because tan is really just identically sine over cos. We can find the derivative of cosecant because cosecant is just 1 over sine, and we can do the derivative of secant because it is 1 over cos. So basically, we're almost there. We've almost got all these trig derivatives done. We're going to do the reciprocal and tan tomorrow, which is going to be very, very simple. And we'll have a review on Thursday, or we'll be playing badminton on Thursday. I'm not sure which. Some of us are going to the Perimeter Institute if we're in physics tomorrow, but that's not until the afternoon. This course is moving along. Once we're done trig, there are 20 lessons left. Okay? No, that's just like, there is no grace. We are completely graceless here. Okay. So, got a couple questions. We'll do those. There is no midterm. There is a final. And then there's reflective journaling, which is all for your own benefit. Okay. Does it count for marks? It does when you get asking for that cloud in heaven. I want to know what the equation of the tangent to y equals x times the cosine of 2x is at x equals pi by 2. Okay. Okay, so I know this whole thing. I know this drill. I know this whole tangent drill, right? I need to know my x and y coordinate. I'm going to use my derivative to find my m. So if you were thinking, I wonder if you take the derivative, the answer is yes. I'm going to plug those all into y equals mx plus b, and I'm going to calculate b. Unless you want to use the point slope of the form of the line, in which case my estimation of u will decline, but only ever so slightly. Okay. To find the y coordinate, Johnny knows the answer. You sub it in. Yeah, so we're just going to sub in the x here. So y equals pi over 2, because x is pi over 2, times cosine of 2 times pi over 2, which mercifully just turns into pi. Okay. What is the cosine of pi? I can never figure this out. Okay. Oh, I know what it is. It's negative 1. So this is really just negative pi over 2. Is it? Yeah, it's negative 1. Okay, good. All right, I know my x, I know my y. So this is going to happen at pi over 2, negative pi over 2. That's where my tangent's going to touch this. So we're on to the, what do you do when you're in calculus? You take the derivative. Okay. Product rule, and I have to be careful because this second function, okay, so this is my f and this is my g, but inside of g is lurking a function of x. It's 2 times x. So sneaky, sneaky thing. Okay. Sorry, I hope I'm not upsetting anyone when I sing the song wrong. So derivative of the first, well, that's just 1 times the second plus the first times the derivative of the second. And the derivative of cos is just negative sine 2x. So I'm doing my chain rule here. So that's the derivative of the outside function. Now I have to multiply by the derivative of the inside function. What's the derivative of 2x? 2. Yes, there we go. Okay. That is a 2-rule combination. It's like a 1, 2, 3 punch. Yes. Okay, so there was a function here, and a function here, right? F and G. So I had to use my product rule. And then this second function G, inside of it, there's a second function of x, 2x. So I have to do the derivative of the inside function. Okay. It's a bit of a jump because I didn't do the u equals this and du dx and y equals something of u. But in the end, it's just going to be a little bit simpler. Okay. All right. So this is going to be cosine of 2x minus 2x times the sine of 2x. All right. There is no need to do any heroic simplification at this point because we're just asking for this value when x is equal to pi over 2. So we're just going to sub it in. So to find m at x equals pi over 2, sub in pi over 2 to y primed. Good. Okay. So y primed, m is equal to the cosine of 2 times pi over 2. I think I know what that is already. Minus 2 times pi over 2 times the sine of 2 times pi over 2. That's a lot of pi. Pi. All right. Those cancel. Cosine of pi, negative 1. I already second-guessed myself a few times on that. Over here, those cancel. Sine of pi. Sine of pi is 0. So that turns into a 0, at which point I immediately stop caring about the rest of the expression. So my slope is negative 1. Okay. Got my x. I've got my y. I've got my m. I'm all ready to go for my b here. So y is negative pi by 2. M is negative 1. X is pi by 2. B is g. I don't know what b is. So negative pi by 2 equals negative pi by 2 plus b. Oh, look at that. B is 0. Okay, so I can work out the equation of my tangent right away, just knowing those things. All right. So that's the first question. That was just a find the equation of the tangent question. Here's the tricky thing. See this pi? It is not a variable. This pi represents a number. It's irrational. So just be careful of it. Don't get in the same room with it. But this pi is a variable, or sorry, is not a variable. Oops, did I say that? It's not a variable. It is a number. So just don't get in the same room with it. You'll be fine. All right, let's do the last one. Johnny, is it time for something extreme like beach volleyball or finding an extreme value? I know what. It's too cold at the beach, so let's just do an extreme value problem. Almost as fun. The extreme value? Oh yeah, that was actually very tricky. Okay. Find the extremes. Oh, find the extremes of y equals cosine of squared of x on the closed interval 0 and 2 pi. Yes, actually, this question exemplifies something that will be on the test. So yeah, something like this. Hey, what should we do? Manuel, you're in physics. You tell me. Yeah, so Johnny, what should we do? Take the derivative? Yeah. Yeah, let's take the derivative, okay? This is continuous everywhere. So we take the derivative. When the first derivative is 0, we have potential turning points, okay? It won't be undefined anywhere, so we don't have to worry about those kind of extreme values. Okay, so y primed is equal to, we had a little bit of a thing here in first period, okay? Cos squared x is this, cosine of x squared. And so this is a chain rule question, once again, okay? So this is a function inside of a function, all right? So my outside function is something squared. So I can just use my power rule on this outside function. So this is 2 times the cosine of x. Now I have to do the derivative of, oh, okay. You want to do the u and all that kind of stuff. Okay, all right. Good enough. So I'm going to take my inside function. It's equal to cosine of x. Take my derivative of the inside with respect to x, and what is it? It is negative sine x. That just rolls out of you so quickly. Makes me proud. Okay, y is equal to u squared. So dy du is equal to 2u. No, 2u. All right. So dy dx is equal to dy du times du dx. Okay. Dy du is 2u, and du dx is negative sine x. But u equals, oh yeah, it's cosine x. It's over there. I don't know why I didn't see it. And so this is 2 cosine of x times negative sine x. All right. I'm just going to move my negative around just to make things even more beautiful than they already are. This is what I do. I just make the world a slightly better place, one erasable chalkboard at a time. Okay, if you haven't done advanced functions, just hang onto your hat. I will write this identity down on the board for you, because this is just a version. This is the double angle identity for sine. It's very closely related to the sum of angle identity that we looked at over there. Okay, so 2 sine x cos x, doesn't matter what order those go in. I want you to look at that because I'm going to give you this as an identity. Okay, so 2 sine x cos x, I didn't make this as beautiful as I could have, is actually equal to sine 2x. And if you're just looking at that for the first time, that's okay. All right. It just happens when you've got like cos or sine squared. This is going to pop out at you. Okay. And to solve it, we need to get it just as sine x or just as cos x, unless tangent pops out of the woodwork. Okay. So here comes our identity. 2 sine x cos x, well, that's just equal to sine of 2x. So that's called the double angle identity. And so this expression over here is equal to negative sine 2x. All right. So now I have the derivative. In order to find the extreme values, I look where the first derivative is undefined or it's equal to 0. So for critical points, I know this is continuous everywhere. So I'm just going to say y primed is equal to 0 for critical points, which are going to be my maximums and minimums. And so negative 2 sine x, or sine 2x rather. I'm just looking to solve that problem right there. Okay. This is a negative sine 2x, but because it's equal to 0, I just don't care. So I'm just going to cross off the negative because I don't want it to confuse me. I'm going to take the arc sine of both sides. So 2x is equal to the inverse sine of 0. So I need to find all those values where sine is 0, and it goes on forever. And oh, it starts at negative infinity, but fortunately, yeah, you don't know what the inverse sine function is? All right. Yeah, yeah, so it's a learning thing. You ready? We're going to find all the values of x that sine is 0 for. In other words, we are finding all the x-intercepts of the sine function, okay? So if I draw it on the board, and I think this kind of helps, right? I think things will start to make more sense, all right? Sine function, what is it? What is it that you say? Sine is, I don't know. Anyway, it starts here, okay? Critical points, sorry, key points at pi by 2 and 3 pi by 2, okay? So there are my 5 key points, 1, negative 1, down here. There we go. Okay, so this does this. Woo! Sure, a fun day today. All right. And it keeps on going like that forever. Poor sine. It is the Sisyphus of the trig identities, okay? So basically, we want to know all the angles where sine is 0. So the arcsine function gives us back the angles where sine is 0, okay? So 2x, arcsine is 0. What's the first place? What's my first x-intercept? Well, it's 0, okay? And next time the sine of the angle is 0 is when the angle is pi. Keep going. The next time the sine of the angle is 0, it's at 2 pi. And even though I have a boundary, I am going to keep going because this is the value of 2 times x. Okay. Here we go. We get back to 0 at 3 pi, and then we get back here at 4 pi, which is similar to floor pi, which is pi that Homer Simpson finds on the floor. Okay. There we go. So 2x takes on all these values. Being cognizant, we're only interested in values of x between 0 and 2 pi. We need to divide both sides by 2, so I'm going to divide everything in this set by 2. And this is going to give me the values of x that solve that. So this happens when x is equal to 0, or when x is equal to pi by 2, or when x is equal to pi, or when x is equal to 3 pi by 2, or when x is equal to 2 pi. Those are all my extreme values, okay? I even have my boundary points here. To really finish this question off, I'd need to plug in all of these into my original function, but I'm not going to do it for now, okay? This is where all those extreme values happen in cos squared x. I just have to find the y coordinates where the extreme values happen. Okay. That was a fast ride for like 5 things that you've never seen because of advanced functions. Okay. But I don't think it's quite as difficult as it might seem. All right.